All right, hello, and welcome to my channel. This channel is for educational purposes, and we like to look at theories of everything and give you a deep dive into what you can do with them, how they operate, and most likely they've been suppressed, and you probably haven't heard of them before. Today is our 466th video that we've done on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an engineer who lived in the 20th century. And around 1959, he proposed his two fundamental postulates, two simple sentences about how the universe operated. He derived a theoretical universe from those two postulates, and kind of an if this then that approach. And so he derived a theoretical universe about what the universe would look like if his postulates were correct. And then he compared his universe with the actual, so-called actual measured universe, empirical universe of the legacy scientists. He does that in part here in this book called Basic Properties of Matter, which is mainly on chemistry. And he compares his theoretical equations, or his equations for many of the basic properties of matter, the compressibility and the specific heat and the interatomic distance and so on, with the tables that scientists have compiled for these values. And it's an interesting study. We're looking at chapter 7 that is on temperature relations. Now, when Larson's two fundamental postulates, the first one is by far more important. The second one is really kind of like what he uses to create his theoretical universe out of the first one. So the first one states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And the second postulate reads that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So Larson uses math and science and logic and geometry to derive his theoretical universe out of a universe made out, not out of matter, not out of energy, but out of motion. And in particular, out of a kind of motion that he calls a scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision a scalar motion with a balloon that you put dots on. If you blow up the balloon, all the dots are moving away from one another. But they're not moving in any specific direction. Rather, they're moving in really all directions. Every dot is moving away from every other dot. And if you contract the balloon, you suck in the air, all the dots will be moving toward each other. But again, in no specific direction. Each dot will be moving away from each other dot. They're all moving in every direction. That's an outward scalar motion that Larson calls the progression, and an inward scalar motion that is analogous to gravitation. And so we've got that scalar motion, and in Larson's system, motion is the relationship between space and time. That's how the reciprocal system gets its name, from the reciprocal relationship between space and time. Basically, motion is a fraction with space or time as the numerator and time or space as the denominator. and that implies a reciprocal relationship between the two. You can see this in speed, our most basic kind of motion. The bicycle is moving 10 miles per hour. 10 miles of space in 1 hour of time. Space over time is speed. But Larson extrapolates this to all forms of motion. They are all of our scientific phenomena are forms of motion. Matter is a form of motion. Energy is a form of motion. Electric charge is a form of motion. Magnetic flux is a form of motion. Surface tension is a form of motion. They all have their signatures in space and time. For example, matter is time to the third power over space to the third power. And that is also part of Larson's first postulate, that the universe is made out of motion, in particular scalar motion. Motion is the relationship between space and time. Space, time, and motion come in 3 dimensions. And they come in discrete units only. Now, there's a few caveats that you need to pay attention to. One is that space and time have no independent existence. They only exist together in motion. And that if you are going to accept the concept of a universe of motion, then you have to accept the idea of motion preceding anything that would be moving. Motion comes before the thing that is moving. And in fact, the thing that is moving is motion. Now, so this goes against 3,000 years of history, where space and time have been seen as the background of the universe, the backdrop from which we go, the stage from which we embark upon our adventures in the universe. We move through space and time, space being stationary, and time is kind of going forward. But in Larson's system, space and time are not the container of the universe. Rather, they are the contents of the universe. Everything is made out of space and time. And motion is always present. Motion is omnipresent and eternal, originating from all locations at all times. And that's what Larson calls the progression. The progression is this outward movement in space and outward in time that occurs at all times in all places. It's really like a 0 point ether, or a null point, a reference point, a state of rest. The state of rest of the universe is to move outward in all directions. And in particular, that progression moves at the rate, again, remembering that space, time, and motion come only in discrete units. And space, time, and motion are in discrete units, and the progression is moving at the rate of 1 unit of space per 1 unit of time, in all locations, at all times. That is the empty universe. That's the universe you have when you don't have anything. And you get things from harnessing that outward motion of the progression by reversing the progression in 3 dimensions. The first reversal is really like the photon. And then that is really like a vibratory motion. And That vibratory motion, its origin is a dispute in the reciprocal system. Some people believe that that is a reversal, a vibration. Some people think that it's a vibration that comes from two rotations. But regardless, once you have the photon, then that needs to be rotated in basically in 3 dimensions, and that gives you atoms. So that's how you get started with matter. Now that progression outward at the speed of light in all directions. The speed of light is 1 unit of space per 1 unit of time. That is the speed of the progression at the speed of light. 1 unit of space per 1 unit of time. And that is the midpoint of the universe. That is what Larson calls the progression of the natural reference system. This is the reference point for Larson's system. This is where he makes his measurements from a moving reference system. Now, there are the stationary reference systems of both time and space. That's where you get your 3 dimensions of space in a still frame, your background or your container universe. 3 dimensions of space in a still background, and with XYZ coordinates, coordinate space, and clock time. Time is progressing. Time is getting later and later and later in no specific direction. So you've reversed the progression in space, but it still progresses in time. And now there's another environment in the universe where the reciprocal happens, and you have 3 dimensions of time in a still frame, and space is progressing. Space is always getting farther and farther and farther apart. So you reversed the progression in time, but space continues to progress. Larson refers to these as the spatial reference system and the temporal reference system, respectively. And these are in what he calls the material sector and the cosmic sector, respectively. The material sector is for all speeds slower than the speed of light. The cosmic sector is for speeds faster than the speed of light. And so the speed of light is a boundary, and when you cross the speed of light, you switch from your stationary spatial reference frame to your stationary temporal reference frame. And now within the material and cosmic sectors, we have subregions that in the material sector, if you have atoms and molecules that approach each other to 1 unit of space, then they can't get any closer, because you have to have a full unit of space before you have space. So they can't get any closer than 1 unit of space. So what they do instead is they move outward in time, because outward in time is equivalent to inward in space by the reciprocal postulate. And so Larson calls this the time region. The time region is the region inside 1 unit of space. And when you look into the time region, first of all, you have to invert the rules again. Now the progression is inward in what he calls equivalent space, or time. It'd be outward in time, inward in equivalent space, because space and time are reciprocals of one another. And we don't see time, we only see space, because we're anchored to a spatial reference system. In the temporal reference system, we would only see time, and we couldn't see space. But that would be if we were moving faster than the speed of light. Okay, so when you cross that boundary, the rules invert, and your perception is also distorted. So what you see in the time region is not exactly what's happening. You are losing something in the translation, and it's a big fraction of what's occurring. Larson refers to this as the interregional ratio. And you have to reduce your results by that amount. You also only see a second power region when you look into equivalent space like that. The same thing happens over in the cosmic sector, except with time and space exchanged. So in the cosmic sector, you have, instead of having the time region, you have the space region, which is the region inside 1 unit of time. And you also have to invert the rules to go over there. And now space, now the progression is moving inward in equivalent time, and gravitation is moving outward in equivalent time. Okay, now the atoms are basically notated by Larson with 3 numbers. Those are those 3 numbers that are needed for 3 dimensions of rotation. The first 2 numbers are really the only 2 that are mandatory, because each one is a 2-dimensional rotation. So the 2 of them together share a 1 axis, and then they also occupy the other 2 dimensions. So you need 2 2-dimensional rotations to get 3 dimensions. But then you can also have an opposing rotation in 1 dimension. That is optional. It's 0 in the noble gases. It's positive in the electropositives and negative in the electronegatives. So you have a 3-number set that comprises all of our atoms. And these are the atoms these are the numbers that Larson uses to come up with his equations for these various basic properties of matter. So we're going to start reading here from chapter 7 on temperature relations, and just pick up the whatever breadcrumbs that you can. He's going to say some things, and I'll try to clarify some of the points involved, but you know, some of it is pretty technical, and you don't need to understand everything. What you need to understand is that this is a general theory. It's a theory of everything. And so the same rules that he's using here for chemistry can be used for astronomy. They can be used for economics. They can be used for metaphysics. And so you're really just trying to get kind of a sense of how he goes about doing this. And then so once you do that, and then you figure out some of the particulars of how the reciprocal system works, then you can use to apply it yourself to whatever subject you'd like. Okay, we'll see how it goes here. The joint action of the 2 ends of an organic molecule that combines their thermal factors, those are the 3 numbers, in this case for temperature. Thermal factors in the temperature determination is maintained when additional structural units are introduced between the end groups. Now, remember here with temperature is the product of every atom or molecule. It's not the property of an aggregate. It's the property of each molecule has its own temperature. And the aggregate is just the average of all the different molecules that go into that aggregate. But the actual temperature is possessed by the atom or molecule. As brought out in chapter 6, such an extension of the organic type of structure into chains or rings also results in the activation of additional thermal motions of an independent nature within the molecules. The general nature of this internal motion was established in the previous discussion. The same considerations apply to the transition point temperature, except that internal motion is independent of the molecular motion in vectorial direction as well as in scalar direction. It is therefore distributed 3-dimensionally, and the fraction in the direction of the molecular motion is 1/8 rather than 1/2. Each unit of internal motion thus adds 1/8 of the 8.98 degrees or 1.12 degrees Kelvin. He kind of derived a lot of this equation in the previous chapter. But basically, each atom has its own specific heat curve. Specific heat is kind of like the rate or the efficiency of energy transfer. How much heat do you have to add to something to add to some matter to raise it by X amount of degrees, to raise the temperature by X amount of degrees. So there are certain substances that you can add just a little heat to and it'll heat the thing up, but then there's certain other substances that you can add a lot of heat and it won't heat up very fast at all. So that's known as specific heat, and most of the specific heat curves are have transition points because of statistics. The atom is going to do anything that it possibly can do to avoid getting to the melting point and becoming a liquid, because the solid state is more probable than the liquid state. And so the molecule or atom is going to make transitions that adjusts the scale of the temperature, the specific heat. So when it goes to a higher level of specific heat, it can take on more heat with less motion in the direction of the melting point. So the temperature will go up, but the atom will not move into the liquid state. And the liquid state is a product of one dimension outside of the time region, while the other two dimensions still remain in the time region, while the solid is all three dimensions in the time region. And the gas is all three dimensions outside the time region. Okay, so to the transition point temperature. So there's various transitions that an atom goes through as it is heated up. And the first transition, ch0, is basically when the beginning of the atom itself. And this first transition point is more or less where where the heat is at 1 unit, and it is it's a significant point because it also relates to the T0, and so the temperature scales are based on this kind of quantized, idealized specific heat curve that each atom has. Each atom has its own specific heat curve, but then you have to also attach it to a temperature scale. Okay, probably didn't explain that very well. I don't have full grasp of the whole concept myself. Okay, with the benefit of this information, we are now able to compute the temperatures corresponding to the specific heats of the paraffin hydrocarbons in Table 21. These values are shown in Table 23, which is right here. So he's got all these paraffins here: propane, butane, pentane, and hexane, and above. And he gives their 3-number sequence at most of them transition to lower numbers. So, for example, hexane starts at 211. After the first transition, it changes to 1.511, and then, then it actually goes back to 211. And then there's a number which is a total, and I do not remember what that number is all about. It appears as if the number is 5, 6, 7, or 8 in all of these atoms. It can be 7.5 also, 5.5. And I do not remember what that number is. So I'm not being very helpful here. Let's just keep moving. And that's generally what you have to do with Larson, is that you're always going to get stuck. You know, don't get stuck on getting stuck. Just keep moving, keep it in your mind, recognize you're probably going to have to go back and look at this again, maybe, you know, in a year or two. And by that time, you will have picked up some other breadcrumbs from other studies of Larson and others, and you'll be able to apply these things. Okay. Endpoint factors, endpoint, melting point, internal total propane. This is still part of that same chart here. Shows the endpoint and the melting point. And then it also shows, I guess, the total number of units of rotation. Anyway, so propane looks like the endpoint of the solid is 81 degrees, while the melting point is 85. Again, because all temperatures are, everything in the reciprocal system is quantized. There's discrete levels of things. There's not a continuum. There's not a continuum of temperatures, in especially in the liquid state, but even in the solid state. In the solid state, it appears to be like a continuum because the units are so small. But in the liquid, there's actually different levels, temperature levels, and you're not in between them. You're either on one or the next, or the one above, or whatever. And so when you do get to the end point of the solid, that doesn't necessarily mean that you're at the first point of the liquid. You have to get up to the next level. And so with propane, the temperature at the end point solid temperature is 81 degrees Kelvin, but the melting point, the actual place where it becomes a liquid, is 85 degrees Kelvin. With pentane, you got 137 for the end point of the solid, and you have 138 for the melting point. Now, for some reason, he has pentane here, and he has those numbers reversed, where it's 145 for the solid endpoint and 143. I'm thinking that's maybe a typo, or I don't have an explanation for that. 143 for the melting point. But then he goes through a number of other, I guess these are paraffin hydrocarbons, and octane, nonane, decane, hendecane, and dodecane. And it looks like in all of these, the liquid, the solid endpoint is less than the melting point. So that one exception, I don't know exactly what that's about. I think it might be a typo. The first section of this table traces the gradual increase in the thermal factors as the molecule makes the transition from a simple combination of two structural groups with properties that are similar to those of inorganic binary compounds, except for the joint thermal action due to the short intergroup distance to a long chain of organic structure. The increase in the factors follows a fairly regular course in this range, except in the case of butane. If the experimental values of the specific heat of this compound are accurate, its transition point factors drop back from the total of 6 that applies to propane to 5.5, whereas they would be expected to advance to 6.5. The reason for this anomaly is unknown. At the C6 compound hexane, the transition to the long chain status is complete, and the thermal factors of the higher compounds as far as hexadecane, which is 16 carbons, I think. The limit of the present study are the same as those of hexane. In the second section of the table, the transition point temperatures are calculated on the basis of the 8.98 degrees Kelvin per molecular thermal factor, which is an equation he came up with a couple chapters ago. As shown in the upper section of the table, plus 1.12 degrees per effective unit of internal motion. The number of internal motions shown in column 1 for each compound is taken from table 21. Columns 3 and 4 are the values entering into the calculation of the solid endpoint. Column 5, as the table indicates, some of the internal motions that exist in the molecule at the transition temperature are inactive at the endpoint. However, the active internal motion components are thermally equivalent to the molecular motions at this point, rather than having only 1/8 of the molecular magnitude as they have in T1. This is a result of the general principle that the state of least energy takes precedence in a low energy environment in cases where alternatives exist. Below the transition point, the internal thermal motions are necessarily one-dimensional. Above T1, they are free to make either the one-dimensional or three-dimensional status, to take either one-dimensional or three-dimensional status. The energy at any given temperature above T1 is less on the three-dimensional basis, which this transition therefore takes place as soon as it can, which is at T1. Okay, we're going to stop there, and we will take over here tomorrow. Just hang in there. Pick up whatever breadcrumbs you can, but just try to see the whole picture, because this is a theory of everything, and it can be applied to every subject. Thanks for tuning in today, and have a